Okay, so welcome you all. Good afternoon, everyone, ladies and gentlemen. Well, on behalf of the SP Portugal, I would like to welcome you all to our first webinar in our oil and gas series and the second webinar of the year. Today, the topic is oil-brine rocks interactions and the impact on oil recovery. Today, we have a guest of honor, that is Santiago Drexler. And for me, today is a very happy day, as Santiago was my professor. He was you all. Sorry, sir. Sorry, I apologize. I was echoing with the YouTube live stream. So I was saying that Santiago, he was my professor. He was the coordinator of my undergraduate thesis. He was the coach of my Petrobol team. So for me, having him here is really heartwarming. Santiago had a very terrific career. He holds a bachelor's degree in chemical engineering from the University of Buenos Aires. Then he started his professional career in Coca-Cola as a plant engineer. And after that, he pursued his master's once again in chemical engineering in the University of Oklahoma. After that, he started working in Brazil, in Petrobras, as a reservoir engineer. And then he started his PhD at the Federal University of Rio de Janeiro. And while pursuing his PhD, he was also a guest professor in the University of Rio de Janeiro. And he was also a R&D reservoir engineer. After concluding his PhD, he started working at Halliburton, where he is the principal reservoir engineer at Halliburton. So Santiago, the floor is yours. Thank you so much for being here.
Okay, thank you very much, Claudio, for the kind words. Can you hear me okay at this point?
Yes.
Okay, so I'll move on. I'm really honored to be here, and it's my pleasure to receive this invite. As Claudio said, our history is very long, and we have a lot of things in common. So I'm very, very glad to be able to discuss these topics with all of you today. And I must say, for this first talk, I won't be presenting any specific Halliburton solutions for this. So the idea here is to have a more academic discussion and show some of the research and of the development that we have done basically in oil rock brine interactions, and we will talk a little bit about how they impact oil recovery and how why this is important for reservoir engineering in terms of not only EOR but also water flooding and recovery in general. So let me start with our agenda today. So as a culture in Halliburton, we will have a safety moment. Then we'll talk a little bit about oil recovery, some fundamentals and some ideas to get everybody on the same page of what we are going to discuss. Then wettability, some definitions and some procedures in the industry, and then what's the impact on displacement. And then in the end, I brought just a case study to see how we really need to account for this when we are doing dynamic modeling for any type of reservoir. Even when we think it's very simple and very straightforward, wettability and its assessment can always be a challenge. So first, let me start with the safety moment. And this is very obvious and is very straightforward, but also is very important, because usually when we talk about safety, we usually think about precautions and knowing the risks and what can I do to avoid risk or to minimize risks. But it's really important that we don't get a passive approach towards safety and also have an active approach. So it's really, really important to take responsibility to our hands. And it's not only talking about work, also talking about our personal lives. When you see some situation that you think it could lead to risk, it could be unsafe, don't keep it to yourself, or don't only fill out the safety report in your company. Speak up, explain to the people why you think it's unsafe, why we need to correct this, why it's important to take safety into our own hands, and why safety is a matter that is important for everyone. So with that, I'd like to go to our technical discussions. And first, well, we start with oil recovery, and since this is a very general audience, we can have people who are still students at the undergrad level, we can have young professionals, we can have some more experienced folks, and we can have also graduate students. So I try to put this in a kind of a general level, and then going deep in some different points for the guys that have some more knowledge. We expect to give some basic reservoir engineering definitions, and then see how we can use them. So after exploration, appraisal, and the static modeling of the field, and when we get to actual production, this type of chart is really well known by anyone who has opened a reservoir engineering book, because we usually, when we follow the books, what we have is 3 stages of recovery, what we call the primary recovery of natural depletion, based on the energy of the reservoir, or the natural energy of the reservoir, basically the pressure. And then secondary recovery is what we call a pressure maintenance. And finally, any tertiary recovery or EOR methods that will want to increase what we can take out of the reservoir, right? Of course, this if we follow every stage, this will be the life of the field, and then we have the decommissioning and abandonment of the field. This is everybody knows that now this is not always the case, and we don't necessarily go through all these stages in the life of a field, and we can start with pressure maintenance, or in some cases like heavy oil, we can go straight forward to enhanced oil recovery. But talking about enhanced oil recovery, what is our purpose? Because nowadays we really have a lot of technical talks about enhanced oil recovery. For the last years, there has been a lot of research. It's a very, very wide field. So when people talk about EOR, we are not usually talking about one area of expertise. It combines a lot of different areas of expertise. But what is the interest there? When we talk about the depletion of the field, here we get to this curve of production rate and cumulative oil. We see the depletion here would be, if we are talking about secondary recovery here, we have this curve A to B, and in B, it would be a time for evaluation of going forward to an EOR process. And what is the difference that this EOR process would make? Well, basically, incremental oil at the economic rate cuts would be how much more oil, how much more resources we can get out by using this type of mechanisms, right? And I know this is kind of a theoretical curve, but the idea would be to have a forecast that would be, what if we continue just with pressure maintenance, we will get up to this point of cumulative oil produced at the economic rate. And then what if we have any type of other process that can enhance production? Then we will have a raise in production, and then we will have later a depletion going through a higher cumulative oil produced. And of course, that would be lower residual oil saturation in the end. But what does it make? Why is this interesting? Of course, we want to increment the oil of recovery, and in the end, it's always about profit and about resources and about not only economic profit, but also in terms of how we can sustain the life of the field. How can we make it more interesting and make use of the resources in having a better way? So it's actually about optimization, both economically, environmentally, and in a sustainable way. And yeah, of course, if we want to get more oil and also make more money and make better use of our resources, there has to be drawbacks, because otherwise we would be performing EOR projects in every well, every field, and that's not the case, So of course, these are technically challenging, so we need investment both in operations and infrastructure, and also we need, if they have risks, because most of the projects, depending on the environments, they will challenge the actual technologies that we have. So we don't really have robust modeling for this. In many cases, we have a lot of uncertainty involved. And we also face challenges, right? For example, if we are going to inject CO2, we need to have the resources for that. We need to have the infrastructure, but also if we have an old facility, we need to make changes in that facility. We need to adjust logistics. So it has an investment. So the return, it has to be greater than the investment in all ways. And that's where I want to say why it's important, what we are going to discuss today, because in a very realistic way, when we apply not only EOR, but reservoir development at any point, the wettability, or what we call rock fluid and fluid interactions, I added fluid here, but I'm gonna talk about rock fluid for the most part of this talk. And it's one of the greatest uncertainties we have for complex environments. And usually we can adjust our parameters, we can try to estimate in the better way possible, but as we will see, it's something very complex. And it's very hard to get an extension of the results we have for similar conditions, similar fields, or whatever we find for similar case studies. We usually need to take the conditions of each reservoir, the fluids, the rock, and everything matters. And in order to build more robust models, in order to get better estimations, better forecasts, and also be prepared for challenges, because also when we don't know what to expect, we can have a misunderstanding, or we can have a wrong strategy that can end up in really damaging the field, or really having poor recoveries in the end. So for that, we will see that it's really important that we take this into consideration, particularly when we have some complex scenarios that are not well known. And as a reminder for most of the people who took a reservoir engineering class, but also for people who are not in this area, we usually, when we talk about oil recovery, we talk about recovery factor, and that's what the typical number that that everybody uses to talk about potential that we have and what we expect, and then also how are we doing in terms of extracting oil and making a safe use of the resources the better way possible in a not only conscious but also effective way. And the definition of the recovery factor is the production of oil at standard conditions over the oil in place. And that would mean whenever we know how much reserves some field will represent, what do we expect to get after the life and of course, this is something dynamic, right? But where do we expect this field to be in terms of resources recovered? And for that, usually we have two components for the recovery factor. And one is what we call the sweeping efficiency. That is this guy over here. And then the other one is what we call the displacement efficiency. That is this guy over here. And of course, what we want is to improve the recovery factor. That means to increase it. And by that, as we see, these two factors are multiplying over here. That means that we cannot completely neglect one of this efficiency if we want to have an efficient recovery. So I'm going to talk a little bit about what each one of these two guys are about. So first we have the sweeping efficiency is what we call the macroscopic efficiency, and it has two components: the aerial efficiency and the volumetric efficiency. So the aerial efficiency, it has to do mostly with the mobility ratio, that is this parameter over here. that is actually the ratio of the mobilities of the displacing to the displaced fluid. So most commonly is the mobility of the aqueous phase that we inject over the mobility of the oil phase that we want to displace. And the vertical efficiency, it has to be with the presence of layers and the vertical heterogeneity. So whenever we have a difference in impermeability mostly and heterogeneities and connectivities across the layers, we can expect to have different sweeping and different efficiencies across the different layers, and that would mean decreased sweeping efficiency in global when we have trouble sweeping the total pay of the reservoir. On the other hand, we have the displacement efficiency, and it's this guy over here that is what we call the microscopic efficiency, and that's because it's more associated with what happens in the pores, at the pore scale, at the pore level. And as you see here, it's more related with the amount of oil, saturation of oil I have initially, and then the residual oil saturation, or the final oil saturation that we'll have after injecting water or after the procedure that we are doing. To understand these microscopic effects, we usually use the capillary number. There are many definitions of the capillary number, but this is at the pore scale level. Then we have some others that includes the capillary pressure and other definitions. But in general, when we talk about displacement efficiencies, we want to talk about ratio of viscous to capillary forces. And at the pore scale level, we have the viscous forces represented by the velocity and viscosity of the sweeping fluid, and the capillary forces basically are represented by the interfacial tension between oil and brine and the wettability that it takes place at this angle here. And then we will talk a little bit about what's the idea behind this. But talking about efficiencies, sweeping efficiencies, and why does wettability matter for this? Well, taking the easiest way out and just talking about the general modeling here, we have the simplest way to look at this is way by the frontal advanced theory. And here we have an injector and a production well. And usually for this theory, we will have a 1D displacement. So for this, what we do is here we will have a water flow over here, and we will divide the distance between injector and producer into two parts. A water invaded zone, that is the part that has already been swept, and the non-invaded zone is the part that doesn't really know what's going on here, what's coming here. So this is actually at initial conditions. And we need to separate this because usually when we calculate the mobility ratio, we consider the mobility of the water phase at the invaded zone here. So we will evaluate the relative permeabilities at an average saturation. That would be this guy here, and it's called up to the breakthrough because we know whoever studied this theory that it will be constant up to the breakthrough. And then for the oil phase, we usually use the mobility of the non-invaded zone, so at the initial conditions. And for that, what we have in time, usually it's a mobility ratio calculated at these conditions. But then, as we will see today, the rock fluid interaction has a great impact on this ratio of relative permeabilities at different saturations. So even if it's before or after the breakthrough, we will have to take this into account because our sweeping efficiency will depend on this. And then for the displacement efficiency, well, displacement efficiency, we see it as how much oil can we, is our recovery potential if we had a 100% sweeping efficiency. So basically, if the sweeping was perfect and we have a piston-like displacement, we can access to all the pores, how our capillary forces will allow the fluids to enter the pores. And of course, I don't need to say why the wettability can be important here because it's directly explicit in the equation. So meaning that, as we will see today, wettability and the rock fluid interactions will affect the way that the fluids are distributed in the pores and the accessibility of the sweeping fluid to the residual oil. that's what's shown here. So we have, this is what's called the desaturation curve. And it's actually just a very theoretical curve from the books, but it gives us the idea of what's the relationship between the residual saturation of the non-wetting phase or the wetting phase, depending on which is the phase that's wetting or not, in terms of the capillary numbers. So usually when we talk about water floodings, we are talking about very low capillary numbers in terms of 10 to the minus 7 to 10 to the minus 5. And then what we can see is there is a critical capillary number that we need to overcome if we want to reduce the residual saturation of phases by injecting the other phase, right? Or if we want to displace more of this phase. As we can see here, so typically for the non-wetting fluid, the critical capillary number is much lower than for the wetting fluid. What does this mean? So it means basically that we need to increase the capillary number a great amount of times, 2 or 3 orders of magnitude more in order to have accessibility to the smaller pores where the wetting phase is. So we will see this in some examples as follows. But before we move to actual talking about wettability, just some definitions from the SPE and other sources explaining how confusing it can be to give definitions about EOR, IOR, and the recoveries. So IOR is kind of a broad term that means any method that would change the reservoir mechanisms and increase the recovery up to what we expect it to have. So it can be injecting fluids, but it can also be changing the patterns of the wells or changing the sequence of injections that we have or other type of interventions. When we talk about recovery, well, as I said before, primary usually is the energy of the reservoir, so known pressure support, and secondary recovery is usually water flooding or gas flooding, but for the sake of maintaining pressure and sweeping without any interactions with the rock or the fluid, just maintaining pressure and sweeping the reservoir. But when we talk about enhanced recovery, it's kind of confusing, but we usually talk about injecting fluid, and then it will have any type of interaction at the reservoir level with the rock or the fluids that will result in increasing the recovery. And then these are 2 other definitions that I think are interesting because they sum up what we want to do. Basically, we want to or reduce the mobility ratio or reduce the capillary interfacial forces, or do both simultaneously in order to improve our recovery. And usually we do that as using injecting fluids as an external sources of energy and or materials to recover oil. So with that is kind of a summary, taking all of 3 definitions together, we have kind of a summary of the objectives of EOR. And then we have different type of processes. We are not going to go through any of this during this talk, but I wanted just to say, but typically we have chemical EOR, thermal, miscible, and microbial EOR, and all of these involve different phenomena and different strategies. So wettability has impacts in most of these things and is affected by many of these processes, and it's an important factor to take into account for all the cases. And also for, not only for EOR, right? Also for reservoir engineering in general. So now talking a little bit about wettability. So what's the definition of wettability? I think most of the people heard about wettability and know what we want to say. Usually we talk about the relative addition of 2 fluids when they are in contact with a solid surface. So it's kind of a competition between both to show who has the preferential tendency to spread into the interstitial surface that we have in the pores. So why is it so complex? Well, it's because it depends on phenomena that happens at the molecular level. and it's really influenced by composition of all the phases involved. And as we know, reservoirs are complex environments, so the rock is complex, and it can be heterogeneous, it can be multi-mineral, and it can have a lot of other complications. It's not smooth, it has some roughness, so it can have anisotropy and also heterogeneity. It has different pore sizes and shapes, and that will affect the way the fluids can displace. But also, it's very important to know that it depends on the oil and brine composition. When we talk about oil and brine, we are talking about multi-component phases. So, of course, we talk about hydrocarbon, but then hydrocarbon, the hydrocarbons and the oil phase can include many type of organic compounds, and that will behave differently when they are in contact with the surface. And also the brine is, we always say the water phase, but we know it's not water, it's brine, right? So it has ions dissolved, it can have a different pH, it can have different conditions that will also play an important role. And then also it's important to say, but we usually say the contact angle, we say a measurement of the wettability, but then what we usually have is distributions of wettability. We, for many cases, the most heterogeneous or the typical cases that we find in real life, we have a variable wettability, and that has to be considered in the modeling. So that brings uncertainty. Usually we need to characterize the wettability alterations in the regions of interest and see how much uncertainty we have with the changes in wettability that we will face, because most of the times in modeling, we won't take this very complex phenomena at the molecular level, right? We will parameterize this in a reservoir, in a relative permeability curve, and then these effects have to be included in that. So we need to foresee how much uncertainty we will carry whenever we do this. We use these relative permeability curves depending on the complexity of the reservoir we have. So then again, in the books, when we talk about states in wettability, there is a classification, and this is usually more to understand, not so much to classify in names, but more to understand how we expect the fluids to displace. And then what we thought that it was the most common, or at least it was thought it would be the most common the past years, was the water wettability. And there is this misconception that people usually say that, oh, all sandstones are water wet, so we only care about water wet scenarios. But we know nowadays, we really know that it's not the case, and it depends. Not all sandstones are the same. They can have clays, they can have different minerals, and not every oil there is the same. So I will show there that in the following slides that it can be really variable. But talking about water wettability, usually the majority of the surface is covered by the aqueous phase, and that will mean that this phase will occupy the smaller pores, and then the oil phase will occupy the larger pores. Why is that? Because it will avoid having contact with the most of the surface area of the pore. So the greater pores are where we have the greatest volume per unit of area. And then what will the water do? Actually, it will only be in the dead-end pores or the smaller pores. No, it will form films like this, avoiding the contacts of the oil, the ganglions of oil. And these ganglions of oil can be actually connected. They don't need to be isolated. But then whenever we inject water and we increase the saturation of water, we will have a discontinuity here, leading to what we call the residual oil, where whenever this oil is here and get trapped by capillary forces, and we cannot really move forward, displace it anymore due to the high capillary number requirement. So when we go to oil wettability, it's actually whenever we consider the opposite case, and in this case, we will have films of oil covering the surface of the greatest pores, and then we will have a phase of water that can be connected throughout the reservoir. And then in this case, we will have the smaller pores full with oil, and the ganglions full with water, right? So, and then if we have the situation where we are reinjecting the organic phase again, we could have isolated blobs of or droplets of water throughout the reservoir. And then we have a fractional wettability. Basically, it's a heterogeneity of wettability. This is very, very common. So it's not actually a category, but it's basically whenever we have different regions with different mineralogy, so and different conditions that make portions of the reservoir that need to be modeled as water wet, and some other portions that need to be modeled as oil wet. So with that, we can have changes in the minerals that are exposed on the surface, and with those changes in composition, we can have different wettability throughout the zones of the reservoir. And finally, what we call as a special case of wettability is the mixed wettability, where we have a small pores filled with water and in water wet condition, and the larger pores filled with oil. And this is actually a result of the migration during the primary drainage, and where the pores with higher restrictions of the smaller pores with higher capillary pressure restrictions remain water wet during the whole stage. So even if we have some changes in wettability through the oil displacing the brine in the primary drainage, we don't see it as a general term through the smaller pores. Okay, so the contact angle basically is a representation of wettability, and it's the most visual representation that we can have. That doesn't mean that it's the most accurate representation of the contact angle we can have, of the wettability we can have. And we know that usually we talk about contact angle distributions, and there is a lot of research that does contact angles at the restored rocks, and that dynamic contact angles and static contact angles. And also we have research that does contact angles in the pore system throughout tomography or X-rays or any other type of imaging, and then where we can separate the fluids and we can actually see the meniscus and assess the wettability in those images. So there's a lot of discussion about this, but for this talk, we are going to use it as a theoretical measurement of the wettability because it's very visual. Actually, why do we use this? What does it mean, this contact angle? When we have a force balance between the interfacial forces when we have an oil water rock system, and we have, for example, here we have a droplet of water, and we have surrounding of oil, and we have a surface. Each one of the interfacial forces will try to minimize the area, right? We know that that's the action of the interfacial tension, to minimize the area of contact in each phase. So with that, we will have a balance between the forces that are trying to stretch this rock and spread out, and the forces that try to make it compact and try to minimize the exposed area. As we have this in a plane of the surface, we can have this balance of forces where we have the oil solid interfacial force, and then the water solid, and then we have the projected oil brine force with the cosine of the angle. So actually the angle will be the angle tangent to the droplet that will be that can be measured through the inner or the outer part, and then we will see what we usually use in the petroleum industry. And then we can also have this in terms of energies of interaction. So basically it's the same way of thinking whenever we want to see when the angle will be greater or lower, depending on the energies of interaction, difference of energies of interactions between the water and the solid, the oil and the solid phases. So which one interacts greater with the solid phase will give a higher or lower value depending to this equation. And in the oil industry, we usually go through contact angle measurements. There is a standard way to do it, and we usually do oil brine contact angle measurements, and if this is an oil droplet and this is a brine, we usually measure the contact angle through the denser phase, and that means through the aqueous phase. And with that, we can say that the lower this angle, the more water-wet behavior we will have for the equilibrium contact angle. So here, this is a classification. As I said before, usually I don't really like to use this as a strict scale of wettabilities. I think this is just to show ranges of where we can consider interactions between the brine and the rock will be greater, and then when the brine and the oil interact in a similar fashion with the rock, and then when we have a greater interaction with the oil phase. So we can see here visually that whenever this angle gets smaller, we will have more water invading this contact, so the water tends to spread more than the oil, right? One thing that is very important is that we usually use this as a characterization of initial wettability to have an idea, but we don't have in reservoir simulators a parameter that will input contact angle, and then we will say, because this is something that is more relevant when we do simulations at the pore scale level. Whenever we want to take the influence of wettability at the reservoir scale, we need to include this in terms of capillary pressure curves and relative permeability curves for the dynamic models. And then something that is important to say is that the equilibrium contact angle can be representative of the interactions at equilibrium, or what we call initial wettability assessment. But then whenever we try to mimic drainage or imbibition, we have a dynamic process when we are increasing the saturation or decreasing the saturation of one of the phases. And then for that, we usually, many people say that dynamic contact angles are the way to model this. So we can have advancing or receding contact angles depending on which phase is moving forward or which phase is being withdrawn, right? So usually whenever we have a water advancing, that means that we have an increase in the water saturation. So the waterfront is advancing toward the surface of the measurement, and that will be more equivalent to what we usually call an imbibition, or an increase in water saturation, and then the receding will be the opposite. Typically, what we see is that the advancing contact angle will be greater than the receding, and that's what we call hysteresis of the contact angle. And the hysteresis means that we won't get the same contact angle for the drainage and for the division. And what's the reason for that? So if the wettability changes, what happens? Well, there are many reasons, but mostly we have the effects of aging. That means whenever we have a surface that was in contact with oil, it won't behave the same as the surface that was completely clean and then in contact with water first. So that will affect the interactions that we measure with this contact angle. But also we have heterogeneities and roughness of the surfaces that says that whenever one phase advances and recedes, it won't encounter the same barriers of energy to displace. Depending on the type of heterogeneities, we need to remember that the Young equation that we use for this, it applies to homogeneous and flat surfaces. So whenever we find roughnesses or whenever we find heterogeneities, we cannot expect to have a simplest and perfect way forward and backwards whenever we compare advancing and receding contact angles. So, and this has an effect in the relative permeabilities and the capillary pressures. I won't be spending a lot of time on this, but we can see obvious effects here when we compare the relative terms here. We can see that the endpoints, starting points, and then whenever we see the crossover points for the drainage and the imbibition curves, they will be different. And yes, of course, if the wettability that we measure when we displace oil by water and when we displace water by oil is different in terms of prior aging and effects of the changes in radius in the pore throats, we will see a different relationship with saturation if we are measuring the curves with the imbibition or the drainage. And also we can see here the curve for primary drainage is the curve number 1. And then the first imbibition is the curve number 2. We can see, of course, we have this hysteresis effect, and this is mostly because this guy over here will represent higher capillary pressures, because at the primary drainage, we usually assume that the rock was completely water wet. So to introduce oil, we will have a greater pressure requirement. So usually whenever you see any capillary pressure curve, it should look like this. So the imbibition has to go below the drainage. And then wettability, as I was saying, this is just a compilation of sources that assess wettability with different techniques. And then, as we see here, we can see different sources give different amounts of water wetness or oil wetness for carbonates, sandstones, or silicates. And so usually the tendency is to say, okay, sandstones are more water wet, carbonates are more wet, but as we saw, and we will see, it will depend on many conditions. Is the sandstone really clean? Does it have clays? Does it have high density materials? Does it have, what is the oil? The oil is polar or is non-polar? How is that carbonate? What's the pH of the brine, and what is the carbonate composition? So it's a complex issue. And what affects the wettability? Well, we have many effects, but these are all, most of them are interrelated. So we can actually talk about all of them together as kind of an interrelation between them. We have intermolecular forces that, as we know, they are always present, and we can have a kind of a stronger interaction depending of the discharge distribution that we have in the surface, and then also whatever we have in terms of composition of the oil phase. How much charge do the molecules have permanent dipoles or not? Do they form hydrogen bonds? Do we have any organic molecule on the surface adsorbed already? For example, an asphaltene that will interact stronger. Also, we have electrostatic interactions, and we know they will depend on the surface charge versus the amount of charge we have in the components of the oil. But it's not so simple, because we know that brine also has charges, it has ions. And usually the composition of the brines, for high salinity brines, means that we cannot apply the DLBO effects of electrical double layers and just get an idea of the type of interaction we will have at the different distances, because the electric constant will be much lower, because we will have a greater interaction, a greater composition of ions and a high ionic force in the medium. And then finally, the acid-base interactions that are also related to charge, but are related to the type of active sites we have on the surfaces, and then the type of compounds that we have in the oil. Are they more acidic? Are they more basic? So this is a very nice summary from Buckley and Liu, a review about the interactions that alter wettability during the aging. And when we say aging, we are referring to the time that we have of interaction between the organic phase and the brine phase. But it's important, and the rock phase. But it's important to know that for these interactions to occur, most of these interactions, that they depend on charge and on charge species. So usually the rock is first in contact with brine, and you equilibrate the ions there with the brine phase. And then whenever you do the aging, you put it in contact with the organic phase, and then you will give some time for these interactions to happen. And when you have a strong interaction between the active sites of the rock and the compounds of the oil, you can alter the wettability from a mineral that would be completely water wet in the beginning. After aging, you can have an oil wet surface. So first we have a polar interactions. So we know what this is. So we have charge distributions, and they will result in positive or negative interactions, and that could lead to attraction of compounds in the oil with different parts of the rock. Also, we have precipitation of asphaltenes. Asphaltenes are dispersed, and they are in a stable colloidal dispersion. But then whenever we have any change in the equilibrium, like for example, we get a more paraffinic concentration of the oil phase, or any other, or dissolution of gas, or anything that can make the effect of resins poorer, and they can hold the asphaltenes in stable dispersion, they can precipitate. And then these molecules, precipitated molecules, they will alter the wettability as well. And then we have this acid-base interactions. We will describe this later, but then we can have acid sites or basic sites, and they can interact with molecules in the oil. And finally, ion binding. We have the ions that will have a high charge density. For example, divalent ions, they could act as bridges, and then surfaces they can attract molecules with the same charge that will be repelled. But then, since we have this positive ion here, for example, they can form this bridge, and the oil can be stuck here, changing the wettability as well. So talking a little bit about acid-base interactions. So we have, first we have let's talk about sandstones. And I need to say that this is in the simplest and most simplified way as possible, because usually we have quartz as its main constituent. But as I said before, we can have sandstones with many different other components on the surface. So whenever we have clays, or whenever we have another minerals that will have a different charge distribution, this situation can change. But assuming that we have a sandstone that will be only composed by quartz, and then we have the pores of this sandstone, and then whenever this surface is in contact with an aqueous phase, it will give place to acid sites. That is what this equilibrium here shows. It is an acid site because it can lose this proton over here, and it can become negatively charged. Usually, the point of zero charge of the quartz is really low. So at most reservoir conditions that are closer to the neutral pH, we will have the quartz surfaces negatively charged. And then why is this important? Well, whenever we have these acid sites, and if the oil or the organic phase has a basis in it, we know that the acids and the bases can react. So we can have this type of attraction between the positively charged the bases and the negatively charged quartz, or the acid-base interaction here. We can have a way to have this molecule being stuck here by the interaction with the active site. But as it's weakens interaction, this could be reversed. So whenever we have, for example, anything that can be changed in the wettability from a base here from the oil, then if we have an acid treatment, we can actually alter this by having a stronger acid that will interact with the base in a stronger way, and that will clean out our surface, and it will become water well again. So that's one of the mechanisms that we can use in stimulation, acid stimulation, whenever we inject acid solutions to change the wettability of the rocks. In the case of carbonates, when we know that they are usually really heterogeneous, but if we are talking about a very model limestone or carbonate rock, we will have calcite as a major constituent, and the calcite will have a basic sites as opposed to the quartz that we saw. So usually these basic sites, they can interact with acid compounds in the same way that we saw for the bases. And then this interaction can be undone by a stronger base. As we saw, for example, here, if we have sodium hydroxide, it will compete with this interaction, and then it will clean out the mineral again. But that doesn't mean that they will always interact with the oil compounds. Well, it depends. It depends on which compounds we have in the oil. And as we'll see here, for this type of interactions, it's important to know the acid and the basic compounds. Usually for the acid compounds, we have carboxylic acids, naphthenic acid, this type of organic acids. And the parameter that's used for quantification is a total acid number. That's basically the milligrams of potassium hydroxide that is required for the neutralization of 1 gram of oil. And we have a standard procedure for titration for measuring the total acid number. Usually, well, of course, the higher the total acid number, the greater the concentration of acids we have. And then for the bases, we usually know that they are nitrogen compounds in most of the cases, and we use the total base number for quantification, and that's sometimes it's kind of confusing because it's expressed as a milliequivalence of potassium hydroxide, but actually the equivalents that correspond to the amount of perchloric acid that is used to neutralization of 1 gram of oil. And then, of course, we have another standard procedure for measuring this parameter of the oil. But then what we'll see is we need to know which type of acid or bases we have, because they are not all the same. And why is that? Because we know that the acid-base equilibrium will depend on the strength of the acid and basic compounds. So sometimes whenever we look into this from the first chemistry book that we read, we know that this is the equilibrium constant between the dissociation of an acid and a base in the aqueous medium. And of course, we know that since this equilibrium constant will depend on the protons and the OH concentrations, they will be dependent on the pH, right? So whenever we want to calculate how much of this we need to resolve these two equilibriums together, and whoever study analytic chemistry, well, we need to do stoichiometry and we need to do the equilibrium equations, and then putting everything together for a certain pH. When we know the constants, we can get how much of each of these species we expect to have. And is that important? Yeah, it is, because that will determine what is the likelihood for any of these guys to interact with the positive active site, or with a negative in terms of repulsion, or the opposite for these guys with a positive active site. So that's what I'm showing with this example over here. That this example is basically for it's showing for a silica surface and this California crude oil that has basic compounds and acid compounds, and then we see here that they have the potential of both the potential measured at colloids formed for this oil, just to try to see the potential of the surface of the oil water distributions, and then we have the potential of the silica surface, and then we'll see for the silica surface we see that it's mostly, as we know, it's mostly negative for all the pH range of interest. And then we see these changes here with the pH. What does this mean? We can see that from 6.8 to higher pH, we can get a negative potential, meaning that we have a stronger effect here of the acid compounds that are negatively charged. And here at the acidic pH, we get the opposite. We have a positive potential, meaning that we will have a protonated basic compounds that will result in a positive charge the surface. So when we join these together, what we can take of conclusion here? Well, we need to know basically how is the surface of the rock charged, how are the components of the oil charged, but also what's the pH, right? Because here, if we are at the neutral pH, we will have some type of repulsive interactions here, but then if we are at lower pH at the reservoir conditions, we will have an attractive interaction. And that, of course, will affect the wettability in the end of the day. And now going to what's more interesting for the reservoir engineers. So, okay, we are talking about molecular interactions, acid-base, and alteration of wettability. Why does this matter? Okay, when we want to see the effects in the well perms and capillary pressures, we will see that it's really important to take into account the wettability. And here we have 3 cases from the book from Donaldson: a water wet, a neutral wet, and an oil wet. Then, if we can see, we start with the primary drainage, but then what is important to see here is actually the imbibition and the secondary drainage, because for the imbibition, the curve number 2 will show the spontaneous imbibition, and then the 3, this forced imbibition. And I will go a little fast here. I don't know if everybody would be able to follow, but then we cannot go back to explain the theory behind this because it will take a very long time. But then maybe we can discuss later. But then we have the spontaneous imbibition, the forced imbibition, and then we have the drainage, the same. And then whenever we want to see what happens here, we need to see what's going on in the curves, in the processes of spontaneous versus forced imbibition for each case. So as we see here, for the water wet case, what we can see here very obviously is that the area on top, the area number 1 is greater than the area number 2, and that is reversed here for the oil wet case. And also we can see here, for example, in the spontaneous imbibition, when we are increasing the saturation of water, we can see that we have a great advance in water saturation spontaneously. And we can see that for the neutral and for the oil wet, we can see that that's not the case. We actually don't have any spontaneous imbibition of water for this case of oil wet. What does all of this mean? Well, it means that I need to provide less energy in order to imbibe or to introduce the water phase in this case than I should do this, of course, because here the rock is soaking water. It wants the water to enter, and here it has a preferential wettability towards the oil. And we will go through this in more detail in the next ones. But then let's see very briefly what are some procedures for measurement or estimating wettability, apart from contact angle that is used as a descriptive way. We have the Amot test, and it basically it uses the relationship between spontaneous and forced imbibition for each of the phases, and it compares to get the value that will give us an idea if the rock accepts spontaneously more oil or more brine. So basically, you start with the plug of the rock saturated with brine, and then you will first do a spontaneous imbibition of oil, and that's kind of the contrary of use of the word that we use for imbibition, but typically for water wet systems we use imbibition for increasing concentration of water. But here it's actually a spontaneous increase of saturation of oil, meaning that we have this plug full with brine, and then oil will enter spontaneously, and some part of the brine will be displaced, and we can measure it here. After that, whenever we have equilibrium and we don't have any other further displacement, we will go to centrifuge or core folding apparatus in order to perform a forced imbibition of oil or forced introduction of oil, and then we will see the maximum amount of water that is displaced, and we will reach what we call the SWI, the initial water saturation or the connect water saturation. And then we will have the opposite way around, but for the brine, and then we have first a spontaneous inhibition of the brine, and then the forced inhibition of the brine, and in the end we will reach the residual saturation. If we measure all the volumes, then in the end of the day we can get a displacement of a parameter that is the displacement by oil. That would be the ratio between the total volume of water that was displaced spontaneously by the oil versus or over the total volume of water that was displaced spontaneously and forced. So the addition of both. And then we have the same parameter for the water. And actually what we do then is the difference between the parameter for the displacement by brine and by oil. And then when we have a greater value here, it means that the water enter more successfully spontaneously. So basically we have a more water wet behavior. Whenever we have intermediate values, we will have a more neutral behavior or intermediate wet behavior. And then whenever we have the lower values, we will have a more oil wet behavior. And then another type of test that is very much used in the industry use the full capillary pressure curve, and we need to get the areas below the curves. And particularly, we are interested in the forced division parts for oil and for water, or the forced displacement part. So the area on top is the area below the oil curve. It represents the forced injection of oil at the secondary drainage, or we call secondary drainage here, the curve number 5. And then here, the curve number 3 represents the forced imbibition or the forced introduction of water. So the area below the curve and this pressure saturation is kind of a PV, a pressure volume curve, and it's proportional to the work. So actually what we mean is that if they are proportional to the work required to introduce the oil phase on the top, or the work required to introduce the brine, the water phase on the bottom. So basically, whenever we have this ratio positive, the logarithm of the ratio of the areas positive, we will have a more water wet condition, and whenever we have it negative, we will have a more oil wet condition, meaning that for this case, we will have a greater work to introduce forcibly introduce the oil, and on the opposite case, we will have a greater work to introduce the aqueous phase. And then something else that we need to consider, and it's very important, and for dynamic modeling, it can be more important, or as important, or maybe more important than the effect on capillary pressure, is effect on relative permeabilities. Here we have an image showing how we can change from the more water wet, the number 1, to the more oil wet, the number 5, the shape of the relative permeability curves. And what we see, well, first, what we usually consider in the lab is that the initial saturation of water, the connect water saturation, when we talk about the imbibition, is typically the same, because we consider that the wettability is altered after primary drainage. So usually they start from here, but then what we see is differences in the shapes, and then in the endpoints that are the final points at the minimum and maximum saturations, and then in the crossovers that are the crossing points, the intersection points for the relative permeability to oil and brine. Basically, what is causing this difference? Well, obviously, if we have an effect, the wettability affects how the fluids distribute in the pores, and what is the capillary pressure requirement, and also how easily the fluids will flow in terms of how easily they will be connected through the greater pores, or how easily they will be stuck in the smaller pores. We can expect that the water wet case will ease the sweeping of oil, because it will make it more difficult to go through the pores, the pore volume for the brine phase, right? So the more the rock likes the water, the more it will try to retain it into the pore space. And that, as what we can see here, usually, sometimes, most of the times, we don't really know the wettability when we are performing this, and we try to see these effects. And then we can have, and this of course is kind of a theoretical comparison again, because we should have exactly the same porous system and under the same conditions, and the only variable should be the wettability, which is most of the times for real rocks is not the case. It's very hard to have a rock that is exactly identical to an analog in terms of mineralogy, pore size distribution. We usually have twin plugs for this purpose, but it's very hard to have 5 rocks that are exactly the same to be able to compare this. But whenever we can, for a theoretical point of view, what we can see here is that the curve number 1, the more water wet, it has the lower endpoint for the relative permeability to brine, and the highest one for the relative permeability to oil. And then we have, for the number 5, we have the opposite behavior. So basically, we can say that increasing the water wettability will have a lower endpoint relative permeability towards brine and a higher towards oil. And then the crossover point will shift to higher saturation. That means that we will need a higher saturation of brine to reach the point where the permeabilities are the same. And why is that? Because brine will have a harder time to sweep the rock, because the rock is trying to retain it, or is increasing its interaction with the brine. So the more water wet, we tend to have a crossover more to the right. There are some QC values. This is just suggested. So of course, each internal lab, they will apply their own conditions, and each reservoir engineering team will have their own ideas about this. But they say typically for a crossover greater than 0.5 and greater than 0.5 are lower than 0.5, depending if it's oil wet or water wet. And then also for the endpoints, for the water endpoint and at the residual oil saturation, that would be here. Usually a value of lower than 0.3 would mean that the rock would be water wet, and greater than 0.5 for oil wet, and then in between will be intermediate. This is not a fixed value, right? This is just some QC. And then for the SWI, they could have some differences. More commonly, this is depending on how are you measuring the SWI. Usually, not for this measurement that we do here for the primary drainage, right? But usually, depending on the type of distribution, if you consider that the rock is completely oil wet or water wet, before or after you can have difference here. But as I said before, usually when you think about primary drainage as water wet, then you move forward to imbibition, considering the real wettability of the rock. And then finally, to finish the presentation, I have a case study just to discuss some of this, to show some of these effects that we see. This is from Brazilian pre-salt, and it's a case study for a WAG case. A WAG is a water alternative with gas. Laboratory case, so there's no modeling here. It's basically all experimental. And what we have in the pre-salt, for who is not familiar with our scenarios here, is carbonate, very heterogeneous carbonates with a very high salinity brines with lots of divergent cations. And then the oil is a very good quality oil, but it will have a great concentration of aromatics, and it will have resins, and it will have a high basic number, but also a non-negligible acid number. So it can interact very, very strongly with the rocks. So we wanted to see how the wettability is in the initial conditions, and then what happens when we introduce carbonated brine for the WAG injection, for the CO2 injection. So as we can see, these are high pressure, high temperature contact angles, and as we can see, both for the limestone, the model carbonate, and for the pre-salt rock, we can see intermediate or oil wet behaviors. Oil wet behaviors for the initial conditions with no CO2, but then when we put CO2 into the system, we are creating carbonic acid, and we are decreasing the pH of the system. So we can see a very dramatic change in wettability is obvious in the droplets here. We can see for the limestone, it goes to very intermediate wet, and then for the pre-salt rock, we have a decrease in the contact angle, but it's not so big as it is in the limestone. And the idea is to understand what happens here. Well, what we can take as conclusions here is there are many things happening here. As we said before, it's very complex interactions that we have. So of course, when we see this, we know that this oil particularly interacts very strongly with the brine at initial conditions. And then when we put the CO2 in the brine phase, and then when we leave this interaction to happen, we change the pH, and then we change the surface charge of the rock. But mostly we have two most important effects here. One is that we will change whenever we have the compounds. We think that even though the acid compounds are less concentrated, we think that were the ones that were changing the wettability here that interacted with the basic size of the calcite. And whenever we change the concentration we change the pH so much, they will get protonated. So the interaction will be really decreased. And also we have the reactivity of the carbonic acid with the carbonate rock. And for that we also, of course, clean the rock. It will dissolve anything that we have H here, and will produce a cleaner surface here. And that's what we see with the decreasing contact angle. And to check this, we perform core flooding for disulfated seawater injection, and then also for carbonated seawater injection. This one is the one that contains CO2. So we can see that for the secondary recovery with water injection, we got a recovery around 50% for plug. And then we get an additional 30% when we switch that. That's in agreement with what we saw for the changes in wettability. And we could see that there is a great effect in the carbonated brine. This is just a low resolution tomography, but just to see the wormhole created by the injection of carbonated brine, meaning that there is a strong interaction between the acid and this carbonate rock here, creating a wormhole. So the conclusion for this would be, for this case, yes, it can increase production, but then you need to take into consideration more complicated modeling that considers the dissolution of the minerals. And also, it's important not to see only the acid and basic number, but also to see how they interact with the specific surface that you have, because in this case, the basic number was greater than the acid number, but we saw that decreasing the pH had this effect. So all of these things have to be taken into consideration. And I think with that, I have the references quickly here. And thank you so much for your attention.
Thank you so much, Santiago, for your presentation. Great as always. So let's start the Q&A. I have already a question here on the chat from Felipe Adrián. The question is the following. With respect to oil flow during water floating, which wettability characteristic is the best one? Because following the capillary number definition, when the contact angle approaches 90 degrees, the cosine in the denominator approaches 0, and then the capillary number is maximized. Would a neutral wet behavior be better for oil displacement than water wet?
Yeah, okay. So for this is actually a very, very hot topic question. And actually I would like to, it's really interesting to discuss this. I will give my own opinions about this, but then I would be happy to hear what Felipe or other people have to say. Because there's no proof considerations regarding this. This is a huge matter of discussion. And yeah, if you take the old papers, you would the old papers, I mean, in the first papers that were using contact angles to describe divisions and drainages, you would say that the optimal condition, and they have a curves that the optimal conditions were up to the neutral point, where whenever you have this disconnection, or you have this dramatic change in behavior, which is actually a very unstable. When whoever did any modeling on the pore scale, you know that this is actually the most unstable thing you can have. So yeah, in terms of this numerical capillary number, usually what has been said would be, well, by maximizing this, we would have to be closer to 90 degrees. But then in terms of displacement, and now we are talking only about displacement, right? We are not talking about sweeping, because for sweeping, we know that's not the most effective way, right? But then if we are talking about displacement, there are some other concerns regarding that. And actually, I have some discussions with very senior researchers regarding which will give us their lowest residual oil saturation. And well, if you take the old fellas that have done these contact angle measurements that I was referring to before, they would say that is the neutral wettability. But then on the other hand, most of the people who done pore flooding and who interpreted the distribution of the fluids, they would say that actually the best condition is whenever you have an oil wet rock, because of where the oil will be. If you could get to a perfect sweeping at an oil wet condition, then you will have a very small amount of oil left, because it will be only these films and these very tiny pores. But whenever you do this in a water wet, you will have these ganglions that have a larger volume of oil. So actually, with that, I want to say, yeah, it's an open discussion. I think I've seen and I discussed theories. In my opinion, I really agree with this. But the thing is that we don't really see this at the field scale, because we would never get to this point, right? These are all theoretical numbers, and we never have the perfect sweeping, and we never have the effect where we get only a tiny film of oil and we remove 95% or 97% of the oil in any condition. So I don't know, Felipe, if I responded I answered your question.
Santiago, Felipe needed to leave because he has another meeting. So
okay.
He wrote it on the chat and he left.
Okay, that's good.
Okay. Then we have another question here. Would you say that the reduction in contact angle is attributed to the IFT reduction or surface charge modification, or is it a superposition of both? I mean, for the carbonated brine injection.
Yes, I think. Well, in that case, actually, I can talk in a more general way, because we did evaluation of both, right? In the terms of fluid interaction, it was not favorable, and that's and for that it's that I know that they actually were the acid compounds that were. I actually have some slides here. I didn't want to take so much in the presentation, but we can see here that that we actually have a visibility of reactivity and changes in the mineralogy and the distribution of the pores by carbonated brine. So I think we cannot neglect this. So it has a very important effect on the contact angle, this reactivity and the change in mineralogy and adsorption that we have. And apart from that, I think we also have contributing the surface charges, because we saw that the acid compounds are really active at this point. So yeah, I think it's both.
Okay. Then we have another question from Yanni Meziane. Hello, thanks a lot for this good presentation. I would like to know how artificial intelligence and Python programming can help for reservoir engineering, especially when you have to face some complex case. I guess apply to enhance our recovery or wettability. I don't know if there is an application of artificial intelligence.
It can be very general, right? But in terms of reservoir engineering, okay, I think we have a lot to comment about how we can use artificial intelligence and how we can use all these more advanced terms. In terms of modeling, well, we use it mostly for optimization, right? Reservoir engineering is mostly about data, right? So for any application that we have large volumes of data and we deal with uncertainty, the greatest accuracy we can get from using robust techniques will enlighten whatever we can obtain, right? So for this, of course, everything that I'm showing here is based on a lot of theory and on a lot of measurements that for you to get an idea, right? We usually take a plug and we say that it will represent the flow unit, and then we will make a measurement of wettability, and then we will propagate that in a dynamic model. And of course, that we then will make that model stronger with history matching and any other type of algorithms that are required for this purpose. So in these terms, we use, for example, we actually have some projects in which we develop optimization techniques for how to improve in our cases, particularly for our scenarios in the pre-salt that are very uncertain and we don't have a lot of databases. So for example, whenever you don't have data, how you can propagate data for these cases? Whenever you don't have, for example, cores available, plugs available, you don't have information on mineralogy. Can I say that these things are analogs or not? And for all that, we really use this type of robust techniques because there is no other way to improve the confidence that we have. So it's really I think at this point it's really ongoing research for how to include this in the dynamic models, but it has a lot of potential and a lot of companies and universities are developing this.
Yep. Thank you, Santiago. So I don't know if anyone has more a question from the audience. So I do have a question, Santiago. I remember a long time ago when I was studying the petrobol, and came a question about Dalmatian wettability, that it was inside a mixed wettability, fractional wettability, intermediate wettability, and then there was this Dalmatian wettability. Have you heard about the Dalmatian wettability?
Yes, I have, and we can actually discuss that. But I always say the same whenever I come to that point. For Dalmatian wettability or for mixed wettability so for me, what people really need to know when characterizing wettability more in terms of what happened to the small pores or what happened to the greater pores, or if we have heterogeneity is it heterogeneity of wettability, or is it a consistent behavior of wettability throughout the pore space? So for me, what is important is that we need to know what affects wettability, and actually that it has not only the mineralogy, the fluid composition, and the characteristic that we have for the rock and fluid, but also about pore size distribution, right? And if you have the same materials, but with a different pore size distribution and pore size heterogeneity, you will find different conditions of wettability. So in terms of fractional wet or in terms of mixed wet, I think it's more a matter of names. And in terms of Dalmatian wettability, is one of the cases as well. But for me, to be honest, what's important to understand is that that we need to consider an effect of scale, right? Because in the end, what is important is how we take this to the reservoir. What's the impact of this spore scale phenomena when we take it to the reservoir scale, right? So that's my view about that.
Okay. Thank you, Santiago. So before closing, Santiago, may you please stop sharing, and the audience, please turn on your cameras so we can take a picture. Okay. The audience can please turn on your video, please. Okay. Thank you. So we'll take it 1, 2, 3. Okay, some closing remarks. We will have our next webinar on the second half of May. It will be about digital rock physics, once again with Santiago Drexler and with Caroline Mignoc from Halliburton. We have 2 more webinars on the pipeline, one about enhanced oil recovery, half and puff, and the other about carbon capture, utilization, and storage. So please stay tuned, follow us in our social medias, and don't miss this event. Once again, Santiago, on behalf of DSP Portugal, thank you so much, and enjoy your Friday. Have a nice weekend.
Okay, thank you so much for the invitation. Bye-bye.